everyone. Thank you for joining us. We'll wait a few minutes until everyone's here. Hello, everyone. Thank you for joining us today for this new webinar. Today, Bruno Charletti, Fluigent's application engineer, will be presenting concepts of microfluidics. Just a few notes before we get started. If you have any questions during the presentation, please use the panel available from the top right side of the screen. Our team of experts will answer your question right away if possible, or will bring them up after the presentation during the question session. A recorded version of this webinar will be available from tomorrow. The presentation is also available for you to download from the right panel. Due to the current situation, we are still recording our webinars from home. We hope not to encounter any technical difficulties. However, we apologize in advance that would be the case. We'll now wait a short time before everyone's here, and we'll start shortly. Okay, Bruno, I think everyone's here. You can start the presentation.
So, hello everyone. Thank you for coming. My name is Bruno Charletti, as Sebastian already introduced myself. I'm the application engineer at Fluigent, and today I'm going to present to you the concepts of microfluidics. So during this presentation, we'll have first an introduction of microfluidics, and then we will determine in what microfluidic system consists. We'll next have an overview of the physics of microfluidics. We'll next have a focus on droplet macrophysics, and we'll finally see some applications that use microfluidics. So first of all, what is microfluidics? Microfluidics is defined as the science and technology that deals with the manipulation of fluids in the range of microliters to picoliters, using networks of micrometer-sized channels. So as we can see on the left picture, a pipette is injecting a fluid within a microfluidic chip that contain micrometer channels. The fluid will flow through these channels and subsequent analysis will be performed. This is a typical microfluidic applications. So why will we use microfluidics? Well, because the small volumes and the small size that are commonly used in microfluidics bring specific features, such as a reduced sample and reagent volumes, leading to low-cost experiments or with a higher sensitivity, higher reproducibility of the experiment. Also, it is possible to have shorter reaction or analysis times. You can have some specific physical flow properties, finally some fast stability of the applied conditions, such as the temperature and the pH. So these features allow to study some phenomena that are elusive at the macro scale level. Using microfluidics, you can target some applications that benefit from these advantages. So one important effect in microfluidics is the scaling effect. So basically, the surface forces will dominate over the volume forces. So if we take an example here, we see that the gravitational force is proportional to the length of a system as a power of 3. And the capillary forces are proportional to the length of a system as a power of 1. So if we take a system length of a microfluidic device, which is 10 minus 6 usually, you see that the capillary force will remain 10 minus 6. And if you use a gravitational force, you will see that the force will be proportional to the length as a power of minus 18. So at some point, the capillary forces will be dominant over the gravitational forces. So the conclusion here is that forces that are negligible at the macroscale level will become dominant at the microscale level. So using microfluidics, we have some physical differences from macroscopic devices. So the miniaturization will bring some advantages, but also some drawbacks. So microfluidics can be observed in many phenomena in the nature. For instance, here we have the devil lizard who lives in very desert environments. And in order to hydrate itself, this lizard only needs to stand on a puddle of water. And thanks to the capillary action on its scales that act as microchannels, as we can see here, the water will flow from the feet through the mouth, and the lizard will be hydrated. Another example is in the human body, in capillaries, for instance, where there is an exchange of material between the blood and the surrounding cells. So many researchers want to reproduce these microenvironments, and this is what we call biomimetics, for instance, to have a better understanding of the human body. And some products make use of these principles. So one very common product is the inkjet printer, when micrometer droplets are generated in parallel. There's also the point-of-care diagnostic systems, where devices make use of microfluidic channels and the capillary effect. So these are some basic products, and microfluidics have evolved over the past decade. So microfluidic devices are mainly found in the life science and point-of-care diagnostic fields. As we can observe here, this is the microfluidic devices market as a function of the year on the different sectors. We clearly see that pharmaceutical, life science research, and point-of-care diagnostics are dominant. But other sectors make use of microfluidics, such as the analytical devices field, also the industrial and environmental field. For instance, the cosmetic industry that make use of microfluidics to produce emulsions. So microfluidics is a dynamic sector with continuous growth of research paper and also of end user products. So here is the milestones of microfluidics and its history. So I cannot go through all of them, but we can see that in 1979, the first lab on a chip appeared, which is a microfluidic chip in which specific functions are within a single chip. In 1995, soft lithography appeared, allowing to produce PDMS microfluidic chips. In the 2000s, one of the most important microfluidic milestones appeared, which is Droplet Macrophysics. Then some biological applications appeared, such as the microfluidic cell culture systems or organ on a chip that want to reproduce the human body, the organs of the human body, for instance. In 2007, paper-based microfluidics appeared, allowing to perform low-cost microfluidic experiments. In 2008, 3D printing microfluidics allowed to produce more complex microfluidic chip and also for a larger scale of production. And in 2015, dropcheck technology appeared, allowing to perform single-cell analysis within droplets. So some of the challenges today that microfluidics face are to produce end-user systems and mass production. So now we'll have a focus on what a microfluidic system consists. So usually a microfluidic system will consist in a microfluidic chip. This is where you will perform your microfluidic experiments, reservoir that will contain the reagents or the buffer, the flow controller that will allow to inject the liquids within the reservoir through the microfluidic chip, and of course, a tubing to connect all the components together. So this is the basis of a microfluidic system, but you can also add some accessories such as valves. And if you want to perform live analysis, you can use a microscope, for instance. If you want to automate the whole system, you can use a computer with the software. So this is how it looks like in real life. So you can see here the flow controller, flow sensor, which has accessories, and the tubing connecting all the components together, and the microfluidic chip here. So during this presentation, we will have a focus on the microfluidic chip and the flow controllers. So a microfluidic chip consists of microchannels that are connected together in a specific design to achieve a set of functions. So as we can see here, we have a microfluidic chip to produce a droplet generation. We have 4 similar designs to produce droplets in parallel. Here we have an organ on a chip device. Actually, it is an intestine on a chip device. Also, a cell culture microfluidic chip when you can inject cells, let them adhere within the chip, and then perform media perfusion, and also have a control of the oxygen, for instance, within the chip. Other functions are available, such as mixing, diffusion, particle sorting, and so on. So in conclusion, this microfluidic chip allows to integrate one or more functions that normally require a laboratory. So this is why we sometimes call them lab on a chip. So many materials and production methods exist. For instance, we can see that we have chip in glass or silicon, polymers, hydrogels, paper, or even hybrid materials combining different materials together. Um, different production methods appeared depending on the material, such as photolithography, 3D printing, photopolymerization, and so on. So what is important here is that each material corresponds with important physical properties and microfabrication strategy. So the choice of the material will play an important role in your microfluidic application. Thus, which chip will suit your application? Well, it depends, first of all, on the desired properties you want, such as 3D complex channels, or if you want narrow size channels, for instance, a sterile environment, if you want to perform life science application, optical transparency, if you want to perform optical analysis, and also fast prototyping, if you want to have microfluidic chips in less than a few days. So you also need to consider the type of use. For instance, if it's a research use, you might want to have a lower number of units with higher fabrication costs. And regarding a commercial use, you maybe want to have a higher number of units with a lower fabrication cost. So as a conclusion, the material will dictate the chip properties, but it is also important to consider the end use when you will produce microfluidic chip. So if you want to go further, here is a paper where you can find two tables. So the first table shows the properties depending on the material you will choose in your microfluidic application. So you can find the rigidity of the material, also if you can have the smallest channel dimension reachable, if the hydrophobicity, and also the optical transparency. And the other table relates if a material is suitable depending on the application, such as a bioculture or droplet formation. In my opinion, this study helps to give an overview of the material properties and the possible applications. But my advice here is to perform a careful study on the materials to ensure the great functioning of your specific application. So now we'll have a focus on the flow controllers. So as we said before, the flow controller will allow to move the fluid from the reservoir to the microfluidic chip. So controlling flow rate is very important in microfluidic applications because a poor flow control can lead to less reproducible experiments, such as non-controlled mixing, or you can also damage your cells. So to address this concern, flow controllers can deliver flow and provide fluid control at the microfluidic scale. So three common flow controllers are available: syringe pumps, pressure controllers, or peristatic pumps. So they all have specific functioning, advantages, and drawbacks. So how do they work? Regarding the syringe pumps, a piston is moved by a pump stepper motor here, and the liquid will be injected through the microfluidic chip. Of course, the syringe pump is connected with tubing. So this is a system that is relatively simple to implement, and a large range of quality and prices exists. For pressure controllers, a pressure is applied on the sealed reservoir. As we can see here, a pressure is applied on the reservoir here, and the fluid will be forced to move through the tubing of the system and then to the microfluidic chip for the application. So this system provides an excellent flow control for a wide range of flow rates, and it is possible to have high reservoir. Finally, regarding peristatic pumps, rollers will compress the tubes here periodically, so it will move the fluid in a pulsatile way. So you will have a pulsatile flow, but it is a relatively inexpensive system. So again, here, this is a summary of the advantages and drawbacks of each flow controllers. So my advice here, again, is that you should use the right flow controller for the right application. For instance, if you want to have a relatively medium to high flow stability, a medium response time, and you want to, for instance, to inject small volumes, a syringe pump will be suitable. If you want to have a higher flow stability and a higher response time, and for instance, make use of the pressure control to perform gas injection, you may opt for a pressure controller. And finally, if you don't really care about the flow stability within your microfluidic system, and that you want something that is relatively inexpensive and easy to implement, you can use a peristatic pump. So now we'll have an overview on the physics of microfluidics. I hope I will not lose a lot of people during this part. So basically, microfluidic properties are derived from the fluid mechanics. And the small dimension and volumes that are used in microfluidics will lead to specific properties or marked phenomena of fluid mechanics, such as the laminar flow or the hydrodynamic resistance. These phenomena are really important in microfluidics, and we will have a focus on both of them. So first, the laminar flow. So the Reynolds number relates the ratio of the inertial to viscous force. Fluid density, the fluid velocity, the tube diameter, and the viscosity. If the Reynolds number is low, which is typically the case in microfluidic systems, the flow is laminar. So in laminar flow, fluids will flow in parallel layer with no disruption between them, as opposed to turbulent flow when the inertial forces are dominating, and this is characterized by chaotic changes in pressure and in flow velocity. So under laminar flow, you can control the fluid diffusion, gradient, and mixing. So this allows for precisely tune the contact time between some fluids. And for instance, it is possible to make flow in parallel to miscible fluids, as we can see here. However, as we are lacking from the convection of the turbulent flow, mixing of two fluids can be difficult in microfluidics. So to overcome this problem, some researchers have found some improved mixing methods. A good option is to modify the microfluidic chip geometry. As we can see here from the Fick's second law, the diffusion zone will depend on the diffusion coefficient and also on the diffusion time. So as a conclusion, you can see that you can use the longer channel for allowing the diffusion to happen. Another possibility is to use complex channel geometry using, for instance, grooves or ridges, as you can see here. This will enhance convection within the chip, and this is what we call a chaotic mixing. So as a conclusion here, the diffusion and mixing will depend on the channel geometry and also on the diffusion coefficient here, which depends on the liquids you will use. So you should design your microfluidic device for obtaining the desired diffusion and also mixing. So now we'll have a focus on the hydrodynamic resistance. So this can be thought as the resistance to fluid flow at a given driving pressure. So the simplification on the previous equation we have see here will allow to lead to a simple equation relating the pressure difference here, which is the difference of the outlet pressure to the inlet pressure, the flow rate flowing within the tube, and the hydrodynamic resistance. So the concept of hydrodynamic resistance is often introduced through a hydraulic electric circuit analogy when the pressure difference is equivalent to the potential of an electrical circuit, the flow rate is equivalent to the current, and the hydrodynamic resistance is, of course, equivalent to the electrical resistance. One interesting thing here is that you can perform the same math that you do to calculate the resistance of an electrical circuit to a macrofluidic channels circuit. So as a conclusion here, the flow rate and the pressure difference in a flow conduit are proportional, and the proportionality coefficient defines the hydrodynamic resistance. And the hydrodynamic resistance can be a powerful tool to enhance or even adjust the performance of your flow control system. So as you can see here, the resistance of a system depends on the resistance of your chip, microfluidic chip, and the resistance of your tubing that connects your components. So the tubing is often with a cylindric geometry, and you can see that the resistance of the tubing will depend on the fluid viscosity, but more importantly on the length of the tubing, and even more importantly on the inner diameter of the tubing. Regarding the resistance of a chip, um, it is often very rectangular geometry, and we can also see that the resistance will depend on the length of the chip channels, and also on the geometry as a power 4 of the chip. So you can see here that you can obtain an optimal flow rate or pressure by adapting the resistance of your microfluidic system. For instance, by modifying the size or the dimension of the tubing. So we saw that the resistance is proportional to the channel length. It's inversely proportional to the inner diameter, in this case as a power of 4, and also to the fluid viscosity. So in conclusion, you really need to consider the microfluidic resistance in the experiments to obtain the desired flow rate or pressure. So now we'll have a focus on droplet macrophysics. So droplet macrophysics can be used in many fields, such as the bioengineering field, the pharmaceutical fields, where you can perform cell encapsulation, DNA analysis, or drug screening. The idea behind here is that one droplet can act as a single reactor. You can also use it in the food and the cosmetic industries to produce emulsions or double emulsions. And also you can perform micro or nanoparticle synthesis for drug release, and this is what's called polymerization of droplets. So droplet macrophysics has attracted a lot of interest in the past decades, as it allows highly monodispersed droplet production with highly reproducible complex structures such as double emulsions or multiple encapsulation. As we saw before, single droplet manipulation can be used as single reactors. So this is today an important tool in the chemical and the biological research. So how droplets are generated? Well, droplet generation is based on the use of two immiscible phases, such as, for instance, the oil and water. So the continuous phase is the medium in which the droplets will flow, and the dispersed phase will be the droplet phase. So droplet generation will depend on the fluid physical properties, on the flow rates that will be used, on the device geometry. Some numbers, microfluidic numbers, can help to have a first overview on your droplet generation, such as the capillary number here, which is the ratio of the viscous forces over the capillary forces. So depending on the viscosity, the fluid velocity, and the interface tension, so on these parameters. So the idea here is that you can adjust the competition between the forces to control droplet generation. So three very common chip designs are used to generate droplets. So the first design is a flow focusing design in which the dispersed phase that enters the two-phase junction will immediately break up into droplets, and the droplets will be carried by the continuous phase. In the T-junction geometry, the dispersed phase will be injected from a channel that is perpendicular to the main channel, and it will partly fill the main channel. Some pressure gradients will be generated at this position, and the interface will be deformed, and at some point it will break, generating droplets. Finally, in the cold flow system, the dispersed phase is injected through a small capillary that is centered in a larger capillary. So they are both flowing in parallel, and the droplets are generated by the viscous shear over the dispersed phase. So many droplet generation regimes exist. Here are the three more important. First, we have the dripping regime, in which the droplets are generated close to the intersection between the two faces, as we can see here, here, and here. There is next the jetting regime, in which the droplets are generated a bit far away from the intersection between the two faces. And finally, the stable cold flow regime, in which this is an amplified scenario of the jetting regime, and the droplets are not generated at all, and we can observe co-flow between the continuous and the dispersed phase. So some researchers tried to determine in which regime you are, depending on the properties that we saw before, such as the viscosity, the flow rate used, the interfacial tension, and the channel geometry. And my advice here is that you want to remain in the dripping regime to ensure that you produce monodispersed droplets, because if you are in the jetting regime, you have more chances to be close to the stable co-flow regime, for instance. So to do so, you can adapt the flow rate and the pressure that you're using of both the continuous and the dispersed phases. So once you have produced droplets, if no chemical is added within the organic or the aqueous phase, for instance here, the oil and water, coalescence between droplets will occur. So to avoid coalescence, surfactants are used to stabilize the droplets. So surfactants are usually amphiphilic molecules. So in this case here, we have a hydrophilic head and a hydrophobic tail. So if you add the surfactant in the oil, in the water in oil emulsion, the surfactant will position at the interface between the water and the oil, and this will allow to lower the interfacial tension between the two phases, and then droplets will be more stable. So today, one very common surfactant used is the fluorinated oil, because this is, first of all, an efficient surfactant, and it is also biocompatible, which is very useful for biologists or for the food industry. So here are some typical applications where droplet macrofluidic is used. So first of all, you can use it for single cell analysis, while you will inject a barcoded bead within a cell suspension, and at the end you will obtain droplets containing one cell and one bead. You can subsequently perform gene sequencing of heterogeneous cell population, for instance, with a relatively high throughput. It is also possible to perform digital PCR when you can partition a single sample into different events. Each droplet is an event, and then you can have the measurements of individually of thousands of events. So this will allow to have a lower noise in your measurements, for instance. You can also perform particle production. Well, you can, for instance, produce here PLGA microparticles in a very monodispersed way. And this can be useful for drug release, and you can produce microparticles, but also nanoparticles or core shell particles. Finally, you can also perform droplet cell culture. For instance, you can have several cells within a single droplet, and you can have a control on the microenvironment, such as the nutrients, the gas. You can also perform 3D cell culture if you use hydrogels as a capsule, and you will encapsulate a cell, and it is possible to perform tissue engineering. So now we will see some applications that use macrofluidic today. So the first application is for rare cell detection. So CTCs are circulating tumor cells that can be found in blood samples. So here we have a microfluidic chip that contains magnetic beads, which are coated with antibodies, allowing to capture the CTCs only. The remaining cells, such as the white blood cells or the red blood cells, we continue to flow. So when the CTCs will be captured, you can subsequently perform immunofluorescence analysis to quantify the number of circulating tumor cells within the chip and hence to determine the concentration of tumor cells within the blood sample. So this is a very useful diagnostic marker for various cancers in blood samples. So another important applications, as I already have introduced it before, are organ on a chip. So organ on a chip are microfluidic cell culture devices that contain living cells that are in range to simulate organ tissue. So as we can see here, we have a microfluidic device that wants to mimic the lung function within a chip. So the idea here is that you want to contain many features defining organs, such as porous membranes, a constant perfusion of media, and you can also want to mimic the interfaces between the cells and the tissues. If you want to go one step ahead, you can also connect your different organ on the chip together to determine the organ-organ interactions. So this is a rapidly expanding research area in microfluidics. And finally, another emerging technology are the wearables technology. And microfluidics is a great candidate for wearable devices because of the properties of the microfluidic chip, such as a great mechanical or adhesion properties, microchannels, and a relatively low cost of fabrication. So for instance, here we have a wearable microfluidic chip that you can adhere on your skin to perform measurements of your skin pH level. It can be connected to a smartphone, and this can be useful in the healthcare industry, the sportswear, the cosmetic, or even the drug delivery industries. So where is the field of microfluidics today? Well, there is a constant increase of research and applications, but microfluidics has not yet reached its full potential. So this could be done by two main reasons. Researchers need to consider end users of the devices. This can be done by encouraging the collaboration between the engineers and the biologists. You can also create some manufacturing processes that require less expertise, and it is also important to educate the end users. Microfluidics is also an academic field opposed to a commercially successful tool. So to improve it, you need to adapt the fabrication protocols for large-scale manufacture or to increase the standardization of your system. So here we can see that, for instance, in the nanomedicine products, some difficulties such as the poor stability or the complex multi-step process need to be overcome to translate some products to mass commercialization. So during this presentation, we saw in what microfluidic system consists. So usually in microfluidic chip and the flow controller, um, the choice of the flow controller on the chip will mainly depend on your application. And then we saw some microfluidic principles related to the physics of fluid mechanics. And we saw that fluid mechanics allow to estimate and tune the microfluidic properties. And then we had a focus on droplet macrophysics. And we saw that the droplet can be generated using several designs. And this droplet generation will depend on the geometry, flow rates, and physical properties of the fluids. Finally, we saw some application examples. So with that, I would like to thank you. I hope you found this presentation interesting. I and my other colleagues, Marine Verhulsel and Arno Retz, will be more than happy to answer to your questions. So thank you very much. Oops, sorry. We're waiting for 5 minutes for the questions to come, and we will be more than happy to answer to them. Oh, okay. Hello, thank you for the presentation. Can you tell us about the project that you are currently working on? What is the most perspective application of macrofluidics nowadays? Well, we are working on many applications. For instance, we're working on some organ-on-a-chip platforms. What else? We also want to perform droplet macrophysics, for instance, doing core shell particles. Do you have other ideas of what application we are on? For instance, Marine or Arnaud?
We do a lot of partnerships with our customers, and we also like to work together to have like a collaboration on European projects. So we are partners on several European projects, like Olifab, a famous one that is driven by Fluigent, and others on artificial muscle called Myochip, and another one on diagnostic called Index. So if you want to collaborate with us, we are really open to collaborations.
All right. Thank you, Marine. Next question. What is the stability of the droplets in all three different scenarios you mentioned? What is the possible droplet? What is the possible droplets combined again in the MF channel? Arnaud Reitz, our R&D engineer, will answer to this one.
You have to distinguish the formations of the droplets. So, for instance, if you are in a dripping or in a jetting regime, which will occur after the production, and which is usually depending on the surfactant and the amount of surfactant you put in your carrier fluid. So basically, this is possible that droplets coalesce later in the microfluidics channels, but this can be prevented by using the adequate amount of surfactant.
All right. Thank you, Arnaud. Next question. How does the resistance of a cylinder depend on the material used? Is there some coefficient that is eliminated at some point during derivation? This is, I think Arnaud Reitz will correct me if I'm answering it wrong, but it does not depend on the material of the cylinder. It will depend on the fluid viscosity that will flow within the cylinder. Is it correct, Arnaud?
Well, to correct a little bit, usually we take assumption here that the fluid is in a no-slip boundary conditions at the walls of the channels, which is usually close to be the case. There is a small slipping length, and if this slipping length is negligible, you can actually take this assumption. And in some exotic cases, like using, for instance, carbon nanotubes or very special materials, you can actually make this slipping layer count in your calculation, and this will usually lower your hydrodynamic resistance. But for most materials, the most common ones, you don't need to pay attention to that.
All right. Thank you very much, Arnaud. Next question. What is the best way to detect bacteria in a droplet? Marine, can you answer to this question?
Thank you for your question. Honestly, I'm afraid I think that no, honestly, I cannot really answer the question.
All right.
Sorry.
It's fine.
I'd say that you can either use optical methods or you can use fluorescence. You can have probes to detect like the surface of bacteria or stuff like that. Or you can also use electronics measurements like the resistance of your channels, of electrical resistance if you put electrodes in your channels. And you can have many ways, and I think that to find one that suits the best, you can look up for publications, and we will be happy to help you with that matter.
All right. Thank you very much, Arnaud. Next question. Is it possible to design a chip to model a cancerous tumor? I think it is possible. Marine, can you answer to this question, maybe?
Yes, so actually it depends on what you are interested in. Like if you are interested in the growing of the tumor, if you want to put your tumor in a microfluidic gradient, or if you want to have a vascular system and see how this proceeds around the tumor. So for each of these different systems, you will have a different design. And actually, some chips are also commercially available depending on what you want to look at. And yes, this is it.
All right. Thank you very much. Next question. What is the limit of microfluids? As in, what is the maximum volume that can be used? In my opinion, my guess is that you can use more than 1 or 2, even 4 milliliter per minute. And in terms of maximum volume, if you mean in terms of volume capacity in a reservoir, this will depend on the flow controller you're using. For instance, in a syringe pump, you will be limited by the size of the syringe. And if you're using a flow controller, you can use larger volumes. So maybe Arnaud, am I correct, or do you want to complete this answer?
The limit lays where when your channels actually cross the kind of symbolical limits of 1 millimeter or 500 microns. It's more about basically having channels and being within the laws of microfluidics than actually doing, there's no clear limit, I'd say, but usually we tend to say that over 500 microns, you're not anymore in microfluidics. You're more in microfluidics applications.
Yeah, and another thing is that, as we saw during the presentation, the Reynolds number allowed to determine if you're in a laminar or turbulent flow. And you can consider that if you're in a laminar flow, it is still a microfluidic application, but it should be the Reynolds number should still be around 1. Next question. Do you guys use CFD to model things before you build them? If so, do you have a preferred approach or software for doing this? Arnaud can answer to this question, so I'll let you answer to it, Arnaud.
Usually when you are building new chips, you can design them in a 2D software. that, and there are various in the market that you can try. And if you need to model things, the most common one is COMSOL. And yes, sometimes it's model things before you do, but also sometimes it's Microfluidics allows you to actually prototype very fast, so you can actually make a design and then iterate through different versions to optimize it by the experimentations.
Yes. Next question. Do you have any project involving nanofluidics? Well, nanofluidics is a very interesting new concept in microfluidics, and this is, I think, an emerging feature in microfluidics, and I think it is interesting to perform some project in nanofluidics. Nanoparticle production, yeah, of course, nanoparticle production using microfluidic is possible. And the thing is that we cannot talk in details about our project, so this is why my response is a bit not really an answer. So there is no more questions. We will still wait 2 more minutes for additional questions if there are some. And if we forgot to answer to any of your questions, don't hesitate to write it down again so we can find your question. Also, if you have additional questions after the presentation, of course, as I said before, do not hesitate to contact us at the email contact@fluigent.com. Next questions. What services does Fluigent offer for researchers? Well, we offer many services. So first of all, the main services we are offering are to deliver flow controllers when researchers need to perform microfluidic experiments. They are found in many laboratories around the world. And then we also do some application notes to show how to perform experiments in the most optimal way using our devices. And we also provide some education on microfluidics, as we are doing it today, for instance, during this presentation. And you can also find many expertise web page in your Fluigent web. Do you have any advice regarding multi-phase microfluidic systems? Arno Rates, maybe you can answer to this question.
So one very common multi-phase microfluidic system is Droplet Macrophysics systems. and they are a bit more tricky to actually simulate. So my best advice would be to try them out and do not hesitate to perform multiple designs, iterations, and test various things through the experimentation, because the harder they get to model, the less responses you'll get from your simulations, basically. So my advice is don't hesitate to try and sometimes fail, but always optimize and go further.
All right, we're waiting for the last questions, if there is any. An email, and either our R&D experts or the sales will answer to your questions. Okay, can you recommend Bibliography to design a chip? Well, during the presentation, I have shown some a slide where you can find the table with the chip properties and the chip application. The reference of this paper is available in the presentation, so do not hesitate to go to this paper. And then my advice is that you should use the references from this paper to have a deeper informations regarding the microfluidic chip designs.
Are done with the questions. Thank you everyone for joining us today. Thank you, Bruno, for the presentation. If any other question, or if you want to contact us for quotes or information on products, please feel free to send an email at contact@fluigent.com. The email address is on the chat panel. We want to thank you again for your participation. We hope you enjoyed it. Remind you that a recording of the presentation will be available tomorrow on our platform and on our website. Please have a look at our dedicated page for the list of Fluigent's upcoming webinars. We wish you a pleasant rest of your day, and thank you again. Bye.